Lesson 9.3, Magnetic Force on Current Carrying Wire. The force on a current carrying wire in a magnetic field follows the same ideas as the force on a moving charge, because current is just moving charges. The direction follows the right-hand rule, where again the fingers go in the direction of the magnetic field, the thumb goes in the direction of the moving charge of the current, and the palm is the direction of the force. The force on a moving charge was QVB sine theta. If I divide by t and multiply by t, so I'm not changing anything, Q over T becomes current, and speed times time is a distance or a length. So I'm going to replace those, and so the force becomes current times length times the magnetic field times sine of the angle. And the angle is between the direction of the current and the magnetic field. An application of this are speakers. You have a coil of wire attached to a cone, and then that is enclosed by a magnet. So we have a varying current run through the wire. So at some point, like in the picture at the bottom, the current is going into the wire at the top and coming out of the wire at the bottom. So it's going around like that. Using your right-hand rule, you can see that that forces the speaker cone out. When the current goes the opposite direction, it'll force the speaker cone back. So that's going to make the speaker cone go back and forth. And that pushing back and forth makes the sound. Another application is magnetohydrodynamic propulsion, which is a way to propel boats with no moving parts. Seawater enters a tube under the ship. In that tube are electrodes that run a current through the water. So this only works in seawater, so that it has the salt water, so the current goes through the water. Also in the tube is a strong magnetic field created by superconductors. Using your right-hand rule with the magnetic field and the current, you can see the water is then pushed back. The water being pushed back pushes the boat forward by Newton's third law. This was the big thing of the old movie called The Hunt for Red October, where the Soviet Union had supposedly made a silent running submarine that used this magnetohydrodynamic propulsion. It's also a way you can use to move dangerous chemicals without moving parts. So let's say a 2-meter wire is in a 2 times 10 to the negative 6 Tesla magnetic field pointing into the page. Okay, so our magnetic field is going into the page, so we have it with X's, the feathers of the arrows. The wire says the current is going up, so let's have our wire go up. What is the force on the wire? Well, the formula, force is ILB sine theta. Current is 2 amps. Our length is 2 meters. Magnetic field is 2 times 10 to the negative 6 Tesla. But what is the angle between the wire and the magnetic field? Well, the wire is going up. The magnetic field is going in. So that makes it 90 degrees. Sine of 90 degrees is 1. So I have 2 times 2 times 2 times 10 to the negative 6 newtons. And which way is that going? Well, fingers are going in. Thumb is going the direction of the current. So our force is going that way. So that is going towards the left. Here's another application. What happens when you put a loop of wire with current on it and a magnetic field? Well, here we can see side 1. If we use our right hand rule, so our fingers are that way, our thumb is coming straight up, so then the force would be up. Likewise, side 2 is force down. So this produces a torque, which then would rotate this loop of wire. So it'll turn until it's normal. The normal is here, which is perpendicular to the face. So it'll turn until that normal is aligned with a magnetic field. So it'll end up looking like this. Where here's side 1 and there's side 2. So what is our torque? Our torque is NIAB sine phi. N is the number of loops. I is the current. A is the area of a loop. B is the magnetic field going through the loop. And phi is the angle between the normal and the magnetic field. So if this is our loop, the normal is coming out of it perpendicular to the face of the loop. And if this is our magnetic field, that is the angle phi. The NIA we call the magnetic moment. When the magnetic moment gets larger, then the torque gets larger. So this gives us an electric motor. There's many loops and they carry current and they're placed between two magnets, so they're in a magnetic field. These loops are attached to half rings. So what happens then is the current goes up to the loop. The torque turns the loop until the normal is aligned with the magnetic field. But when it's aligned like that, notice now there's no contact with the wires and the loop because of the break in the half rings. So now there's no more current. So that means momentum will continue turning the loop, and when that happens, the half rings will make contact again and repeat the process, which will cause our loop to continue to spin. So a simple electric motor needs to supply a maximum torque of 10 Newton meters. Uses 0.1 amps of current. The magnetic field in the motor is 0.02 teslas. If the coil is a circle with a radius of 2 centimeters, how many turns should be in the coil? Well, first of all, let's make centimeters meters. So torque is NIAB sine phi. We want a torque to be 10 Newton meters. We're looking for the number of loops. I is 0.1 amps. Our area, it's a circle, so it's pi times the radius squared. B is 0.02 teslas. And what's our angle? Well, the maximum for sine occurs when it's 90. So we're going to use 90 degrees. because then sine of 90 is 1, which is the largest sine can be. All right, multiply this side out using our calculator. And I get n times 2.513 times 10 to the negative 6 Newton meters. So then divide, and I get 3.98 times 10 to the 6 loops. So almost 4 million loops. May seem like a lot, but if you ever take apart a little electric motor, they use very, very tiny little wires, little thin wires, so it is possible.